Hi everyone. So at this point, we've been using matrices. We learned how to do the row operations and use those to solve systems of equations, and we used matrices for that. We learned how to multiply a matrix times a vector, and that gave us a different way of interpreting these linear systems. But at this point, it would be totally fair for you to say, like, okay, I know how to do calculations with matrices, but I don't really have a good sense of what a matrix is. Like, what is it for real? Well, we're going to answer that question, and it's going to be really useful. It's going to give us a better geometric sense, and it's also going to give us some more algebraic tools that are going to be useful. All right, so suppose A is an n by m matrix. When we say that, that means that A has n rows and m columns. Then what we know is that you can multiply A times an m-dimensional vector, let's call it x, and when you do that, the result will be an n-dimensional vector. And if we focus on this role that A plays, we can interpret it as being something like a function. So let's move to a side note and talk about that for a second. Let's say you have a simple function like f of x is equal to x squared. One way to think about this is as a process that takes some number x as input and produces a new number x squared as output. So going back to the linear algebra, we can use this matrix A to build a similar sort of process. We'll call it T, that takes the vector x as input and produces the vector A times x as output. And one thing that's a little bit different from the functions that we were looking at is that the inputs and outputs might be different from each other because the inputs are m-dimensional vectors and the outputs are n-dimensional vectors. So the terminology that we use is that T is a transformation from Rm to Rn. The word function is, I would usually reserve it for the case where the output is a number. And so in this case, the output is a vector, so I wouldn't call it a function. Transformation is the word that we're using. Another term that's commonly used in this context is map or mapping. And then there's also some notation that's commonly used. So when you see this, you actually read it as saying that T is a transformation from Rm to Rn. Okay, so just to illustrate with an example, let's say we have this 3 by 2 matrix. And let's consider this transformation that comes from the matrix. Because A has 2 columns, the input, or the domain, is 2-dimensional space. And because A has 3 rows, the output, or the codomain, is 3-dimensional space. Now, it's a little more complicated than what would have happened in your algebra pre-calculus classes, because in those classes, if you had a function, you would draw the graph of that function. And that graph would allow you to see what the output of the function is for all possible inputs simultaneously. That you really can't do here. I mean, in theory you could, but the graph of this function would be in 5-dimensional space, and so you can't actually draw that picture. So what you can do is you can pick some representative vectors in the domain, and you can draw their images on the right. So I'm going to pick a couple of vectors that are important enough that they have some standard notation associated to them, E1 and E2. E1 is the vector 1, 0, and E2 is the vector 0, 1. So now let's calculate their images. So T of E1 is, by definition, it's A times E1. And so now we can actually do the multiplication and see what we get. And what we get is 2, 0, 1. And then similarly, we can calculate T of E2. And when you do this multiplication, you're going to get 0, 2, 3. Now, it's not a coincidence that the results that we just got are actually just the columns of the matrix. We'll talk about that more in a second. But for now, let's plot these results on the graph. And here they are. All right, so you might not think this actually gives us that much information. There are an infinite number of vectors in the domain, and we've only plotted 2 of them. If you imagine, going back to your algebra class, if I told you what the value of a function f of x was for 2 values of x, that doesn't give you that much information about the function. But these transformations satisfy a special property called linearity that allows you to extract a lot more information just from this little bit of data. And to illustrate that, let's say I wanted to find out what T of 1, 1 is. Well, that's A times 1, 1, because that's the way the transformation is defined. But I can rewrite 1, 1 as a sum, 1, 0 plus 0, 1, or E1 plus E2. And now we can use the fact that this multiplication distributes, which allows us to use the calculations for E1 and E2 to get the answer. Now, if your goal was just to calculate t of 1, 1, it would have been much easier to just multiply A times 1, 1. But this calculation sheds some light on the situation. Because on the domain side, we can plot 1, 1 as being related to E1 and E2 as the sum of the two vectors. And the calculation that we just saw shows that t of 1, 1 is similarly related to 2, 0, 1 and 0, 2, 3 as the sum of those two vectors. And going even further, we can do this for every vector in R2 because every vector in R2 is a linear combination of E1 and E2. So we'll talk more about the geometry of these transformations in the next section. But for now, I want to pin down some algebraic characterizations that are really important. So as was just mentioned, the multiplication of a matrix times a vector distributes over vector addition, meaning that it satisfies this identity that A times x plus y equals A times x plus A times y. It's worth checking for yourself that this is actually true, because we define the multiplication in a weird way. It's not 100% obvious that it's true. It's something that actually needs to be checked. So for example, in the 2 by 2 case, you can actually write down in general form what both sides of this equation would look like and calculate both sides and check to see that they're actually equal. I'll leave that as an exercise for you to do on your own. Another algebraic property is that if you have a scalar that's being multiplied times a vector, then that scalar can be pulled out in front of a matrix. Again, this is something you should check that it's true, but it is true. So now, let's suppose that we define a transformation by this formula that we've been using, that t of x is equal to A times x. Then we can translate these algebraic properties for A into algebraic properties for t. So just directly substituting t of x equals ax into the above equations, we get t of x plus y is equal to t of x plus t of y, and t of kx is equal to k times t of x. And even though these properties look simple, they're actually very special and important. So much so that we make this definition that a transformation from Rm to Rn is linear if it satisfies these properties. And you know how this class is called linear algebra? This is why. This class really is the study of the algebra of linear transformations. But it's worth pointing out that linear transformations are rare in the sense that like most of the functions that you've encountered in your life are not linear. So I'll illustrate with a few examples of just functions of one variable, which you could think of as being a transformation from R1 to R1. So like think about f of x is equal to x squared. That's a really simple function, right? If this was linear, it would satisfy the property that f of x plus y is equal to f of x plus f of y. Is that true? No! Because x plus y squared is not equal to x squared plus y squared. And similarly, if you think about all the other cool functions that you know about, like sine of x, cosine of x, e to the x, square root of x, none of them are linear. So this leads us to a question: which transformations are linear? So what we know so far is that transformations that come from matrices are linear. These are the transformations that have the formula t of x is equal to A times x for some matrix A. And these are definitely linear because that's where we got those conditions in the first place. But we also know that lots of transformations are not linear, including lots of interesting functions like x squared, cosine of x, e to the x, etc. So what other linear transformations are there besides the ones that come from matrices? And this question is answered by a theorem that says that a transformation is linear if and only if it satisfies t of x is equal to ax for some matrix. So in other words, the transformations that come from matrices are the linear transformations. There is nothing else. And so in my mind, this answers the question of what is a matrix for real. It's not just an array of numbers. The right way to think of it is that it's a linear transformation. And so while it could be useful to keep the notation distinct, so we will still write t of x is equal to a times x, and we'll technically view t and a as being two different types of things, there's a dictionary between linear transformations and matrices, and that dictionary is flawless. There is nothing lost in translation. So in order to prove the theorem that was just stated, we need to prove that a linear transformation comes from a matrix. We already know that the transformations that come from matrices are linear. Now we need to prove the other direction, that if a transformation is linear, then it comes from a matrix. So first of all, some notation. In R2, we saw earlier that there are these special vectors, E1 and E2, and we used those to some advantage in an earlier example. In R3, there are three special vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, and those are called E1, E2, E3. Notice that there is a little bit of a conflict of notation where we're using E1 and E2 to represent different things depending on what dimension we're working in. And so it's really important that we have the context established, that we know we're talking about two-dimensional vectors versus three-dimensional vectors or so on. And so more generally, in Rn, you'll have n special vectors, E1 to En, where each of these vectors has a 1 in one entry and zeros everywhere else. So one of the things that's special about these vectors is that if you have a matrix A and you multiply A times E1, you get the first column of A. And similarly, A times E2 is the second column of A, and so on. And so what this means is, let's say I have a matrix, but I don't tell you what it is. You could ask me, well, what's A times E1? What's A times E2? And just from knowing what you get when you multiply the matrix times these special vectors, you have all of the columns of the matrix, and so you have enough information to write down what the matrix is exactly. Okay, so now, let's suppose we have a linear transformation, T, from Rm to Rn. In this case, the domain of T is m-dimensional, so the special vectors that are there are E1 to Em, the m-dimensional special vectors. So I could plug these special vectors into T, and then I get T of E1, T of E2, and so on. And these are all vectors in the image of T, so that's n-dimensional vectors. So then I can take these vectors and make a matrix out of them, and call it A. This is an n by m matrix because it has n rows and m columns. So my claim is that this is the matrix we were looking for. This is the one that satisfies T of x is equal to Ax for all x. And so that means that T is the linear transformation that corresponds to A. So to prove the claim, we start by writing x out, and we observe that we can actually write out this vector x as a linear combination of these special vectors. And now we use the linearity to separate the terms and pull out the scalars. And now we observe that this expression, x1 times t of e1, and so on, that expression is exactly a times x in the column picture, where a times x is a linear combination of the columns of A. All right, so that completes the proof. So the moral of the story is that linear transformations and matrices are essentially the same thing, and that gives us the ability to go back and forth between the two perspectives whenever it's more convenient. And in the next section, we'll use this to write down explicit formulas for matrices that do interesting things from the geometric perspective.